Our next application of multi-objective least squares is something called regularized data fitting. It's a very powerful method to improve fitting models. So let's start with the motivation. So let's consider fitting a data model that of some relationship that we guess holds, like y is about equal to f of x. F is some unknown function. And what we'll do is we'll use a linear in the parameters model, and that looks like this. We will choose basis functions f1 through fp of x. And then what we'll do then is we'll fit to the data the parameters in the model that multiply these basis functions. That's going to be theta 1 up to theta p here. So that's going to be the idea. And we're going to assume here that f1 of x is 1. It's the constant. That's very common. And that means that this first term in the model is just theta 1. People refer to that as the offset in the model. Okay. Now, recall that one interpretation of what theta I is it's how sensitive our prediction f hat of x is to fi of x. So for example, if I told you that theta 3 equals 0, you would conclude that, in fact, f sub 3 of x has no effect whatsoever on our prediction. On the other hand, if theta 4 were, for example, extremely large, that would mean that for just small changes for very small changes in f4 of x, in the fourth basis function, if very small changes in that would lead to very big changes in the prediction. In other words, it would be very sensitive. Our prediction would be very sensitive. Now, the idea here is that that's a bad idea. Oh, I should mention one thing. There is an exception. If we look at I equals 1, theta 1 multiplies a basis function that's constant, and which is absolutely constant. It doesn't change. So theta 1, which is the offset in the model, cannot, we don't interpret that as a sensitivity. Okay, so the conclusion of all this, and this is all very rough, it's just basic intuition, is we do not want theta 2 up to theta p to be large. And if someone says, why don't you want them to be large? You say, well, that makes, the larger they are, the more sensitive my model is to what the values of these basis functions is. Okay, that's the idea. Oh, we don't care about theta 1. Theta 1 can be whatever it wants to be. Okay, so this is all vague, but this is the motivation for regularization. And so what we're going to do in regularization is just have two objectives. One is going to be the traditional least squares fit on your data. And the second is going to be that we would like theta 2 to theta p to be small. Okay, so let's suppose we have a training data set. And what we're going to do is we are going to express the error on this training data set as a theta minus y. These are capital N vectors here. So these are the N vectors consisting of y1 through yn on the right hand side. That's this one, and this on this thing is y hat evaluated at x1 up to xn. Okay, and the matrix A, remember, is something like the basis functions evaluated at the data points. All right, so regularized data fitting goes like this. You start, the primary objective is the usual least squares objective. It's this, that's the sum of the squares of the prediction errors. So we obviously want that small. And in fact, in least squares, simple least squares data fitting, you simply make that small. That's what least squares data fitting is. We're going to make a bi-criterion problem. We're going to add a second objective. And the second is, this one says, this is the sum square of the prediction errors. This one says, at the same time, I would like the coefficients theta 2 up to theta p to be small. And we do this. And lambda is called the regularization parameter here. This is called regularizing the data fitting procedure. Okay. We'll talk about how you would choose lambda in a minute. Now, for a regression model, this turns out, this has a very simple look. It's simply here, y hat is explicitly x transpose beta. X is the data matrix plus nu times 1. That's the vector of all ones here. And what we minimize is this. That's the vector of y hats. And then here, what we do is theta 1 is v, and we don't we don't regularize, but we do regularize the other, which is beta. So we simply make this thing up here. Now, here, let's mention a couple of things of what happens, right? When lambda is 0, you recover just least squares data fitting, period. That's it. You minimize the sum of the squares of the prediction errors, end of story. When lambda gets really big, this whole thing, you're basically saying I put a huge cost on having the coefficients theta 2 to theta p being non-zero. And so basically, as lambda goes to infinity, theta goes to the theta 2 to p goes to 0, and theta 1 actually is going to go to the mean of the data, because what it means is that when lambda is really big, this reverts to the constant model. And remember that the best constant model of some data is the mean. And by the way, the mean square prediction error is the square of the RMS value of y. Okay, so that's what that does. Oh, another word for regularization is shrinkage. That's used in statistics, and the reason is pretty clear. What it does is this serves to shrink the coefficients to make them smaller than they would be if you didn't have that term. Okay, now how do you choose lambda? Well, here there's a very good way to do it. What you typically do is you would actually build your model this way, and you'd work this, you'd do this for 20, 30 different values of lambda. Traditionally, and just as a practical matter, those are spread over a very large range, and they're also typically logarithmically spaced. So you would work out, you'd get 20 different models, 30, something like that, with different values of lambda. You get a completely different model. Then what you do is you go and take that model and you evaluate every single one of those on the test data set. And then you look for the point which has the best test error. Actually, honestly, what people do a lot of times is they choose lambda a little bit bigger than that, because all other things being equal, the larger lambda is, kind of the smaller the theta 2 to p is, and therefore the less sensitive your model is, right? And that's just always a good thing, to have an insensitive model. Okay, so we're going to look at an example. It's a very simple example. It goes like this. We have a true, in this case, it's all made up. So we have a true function, f, y equals f of x. Actually, plus a little bit of noise. So the true function is this something that has this form with a sinusoid, okay, with certain values of theta 1 up to theta 5. Okay, so we generate it, and this black curve shows that. The training data, there's not much, actually. It's crazy. It's these blue dots. So there's just a couple. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we're going to train on those points. Now, let me make a couple things pretty clear here for those blue points. Notice that we don't have any data suggesting this big dip in the function. Not a bit. We don't have any data suggesting it goes like that. So I mean, this is pretty crazy to fit this. Okay, so what we're going to do is we'll fit a model using the train, the blue point, 10 blue points, and we'll evaluate it on the 20 points which are the red points. Okay, and the model is going to have this form. It doesn't matter that the basis functions are sinusoids. It just doesn't. That's not relevant. Okay, so here's what happens, and this is something actually you have to take a good look at it to kind of figure out, make sure how it works. Now, when lambda is super small over here, we're basically doing least squares. That's it, least squares data fitting, and it's not bad. We get I don't know what that is, like that's about 0.2, so that's about 0.05. So basically, our RMS error on the training set is quite low. It's maybe 0.05. On the test set, it's 0.2, which is okay. That's what it is. But then you see something interesting. As we increase lambda, that's moving along here. And you can see this is a good example where I said that we would vary lambda over a very wide range on a logarithmically spaced scale. Okay. So what happens there is, basically as you increase lambda, nothing really happens to the model until around 10 to the minus 1. And what's happening is the coefficients are now shrinking. And of course, the training error gets worse. That's how bijective optimization works, right? That if when you crank up lambda, the second objective gets smaller and the first objective gets bigger. And indeed, it goes up. And then, roughly speaking, for lambda bigger than 100 or so, this is just basically the constant model. So I would presume that these are in fact the standard deviations of the training the test set. Okay, so that's that. But now let's focus on it and see what happens. The training error, of course, always gets worse as you increase lambda. Here's something amazing. Not amazing, it kind of makes sense. Here you see this dip, very characteristic. Sometimes it's much more pronounced. In other words, you really get a much better model with some regularization. In this case, you got a slightly better, or somewhat better model, actually, with regularization. And what this does is it suggests you should choose lambda around 0.1. As I said, sometimes you just take the one that gave you the best test error, but in fact, usually people kind of skew it to a little bit larger because the less sensitive your model is, the better. Okay, and that's it. So we choose that value, and now what this shows, this is called the regularization path. So here we think of the coefficients theta 1 through theta 5 as being functions of lambda, and then that means that they trace out a path or a curve. And we're just plot it. So here's lambda, and here you go. You can see, oh, I should explain this figure a bit. These dashed lines show the true value of the parameters. Now, this is all completely fake, made up data because, and so there is such a thing as the true values of the parameters. They're shown as the dashed lines. So if your estimation method did really well, we would be right on top of those dashed lines. Now, let me point out, the model has 5 parameters, and we fit it on 10 data points. So, we should not expect to do that well. But nevertheless, here's what happens. Up to about lambda equals, I don't know, 10 to the minus 3 or 2 or something like that. It's the same. Something super interesting happens right in here. Right where this is, which is where what we want to do, we think about 0.1, and if we go up here and look at 0.1, you see something actually kind of amazing. What you see is right at about where that dip in the test error dips to its lowest point, right about there, actually, weirdly, our parameters kind of get weirdly close to the true parameters. So that's kind of the idea, and this is what regularization does. This is not a very dramatic example. Sometimes if you have a lot of data, you don't really need regularization. But I don't know. So I've heard friends say things like, friends don't let friends fit models without regularization, right? Because it's just a good idea to do some and if it turns out they don't need much regularization, that simply means that you end up choosing, a value of lambda that's 10 to the minus 5. Then that's just fine. But in many cases, it will enhance a model, the performance of a model very substantially, right? So that's regularized data fitting. I should say that this is really, once you know about least squares data fitting with regularization, you can be very effective at building models, building prediction models, and so. This is really this is enough for you to actually go out and really do well at this kind of stuff. There's a whole lot more for you to learn. A lot of this stuff will be interpreted statistically when you take a course on that and all sorts of other stuff. But this is kind of the basics.